All right, good morning, everyone. I'm going to go ahead and get started on the webinar. Thank you for those that are joining us. I think everyone can see my screen. I wanted to double check that, but I think everyone can. Good morning and welcome to the January California-Nevada Drought Early Warning System Drought and Climate Outlook webinar. Thanks to you that have joined us before and those that are joining us possibly for the first time. My name is Amanda Sheffield and I'm from Scripps Institution of Oceanography at UC San Diego. And I'm the Regional Drought Information Coordinator for NOAA's National Integrated Drought Information System for California and Nevada. Before I get started, I wanted to first thank our speakers and CNAP and the Western Regional Climate Center, who are university partners in the region, which are making this webinar possible today, especially given fiscal year appropriations currently. And I wanted to say a thank you to them and say that all the speakers today on the webinar, including myself, are university employees. So this bi-monthly webinar series is designed to provide the region with timely information on current drought status and associated impacts, as well as a preview of developing climatic events. This webinar is being recorded. A recording as well as presentation slides and a 2-page summary will be available on drought.gov when possible. If not in the meantime, I'll have my email at the end where you can contact me for information sooner, then we may be able to post it on drought.gov. Before we get started with our speakers, just a little bit for those who don't know the background about NIDIS, the National Integrated Drought Information System. We work to provide a better understanding of how and why drought affects society, the economy, and the environment, as well as improve accessibility and dissemination of early warning information for drought risk management. And we do this by working on different regions and building off regional drought early warning systems to build a national drought early warning system. And as you see here in California, Nevada is the region that we sit on and that I work on. Some of you have seen this before, but just a little bit about what is a drought early warning system. This is a network that uses new and existing partner networks to optimize this expertise of federal, tribal, state, local, and academic partners to make that climate and drought science available, readily available, understandable, and usable for decision makers, and improving the capacity of people in our region to better monitor, forecast, and plan for the impacts of drought. We do have a strategic plan and had our first coordination workshop over the summer, and we do have a series of quarterly key stakeholder calls that if you're interested in participating more in the drought early warning system, please contact me. As well as a drought-related activities and resource matrix that we have currently released to sort of learn lessons learned from the past drought, as well as keep going forward with new activities and leveraging off the knowledge we learned in the last drought. So today's webinar, we're going to have the California-Nevada Drought and Climate Status Update first. Julie Kalansky, who's with Scripps and UC San Diego and is also the program manager for the California-Nevada Climate Application Program, will give the update. Followed by Shrad Shukla, who's with UC Santa Barbara. He will be giving the outlook and is also a member of CNAP. We'll have a wildfire recap from the director of the Western Regional Climate Center, as well as a drought update with specific tools from UCLA with Dennis Lettenmeyer, who is a professor there and also a member of CNAP. So with that, give me a second and we'll pass over to our first presenter.
I will go ahead and get started. So I'm going to talk about the climate and drought update. And the 3 main topics I will cover is what you see at the top of the screen. It's precipitation and temperature and what it has been like thus far this water year starting October 1st of 2017. And then I will touch on snowpack and then also reservoir levels in the region. So before we get started, this is the Drought Monitor as of January 16th. As you can see, much of the southern region, both the Southern California and Nevada, are abnormally dry, and the Central Coast in California and far eastern southern Nevada are in a moderate drought. And that you'll see in part is due to a very dry start of this water year for the southern regions. So this is what I was talking about on dry start to this water year. And so this is from the National Weather Service in San Diego region. And this is looking at different rain gauges spread throughout their service area. And so these are primarily in Southern California. And what you can see is that, for example, 2017 from October to December is the second driest year since 1850 in San Diego. In Ramona, it was the driest year since 1974. In Riverside, it was the second driest year since 1893. And in Newport Beach, since 1921, it was the driest year. And so the start to this water year, especially for the southern regions, of California, Nevada has been particularly dry. So now the question is, where are we now? And so what you're looking at is on the left side of the screen, this is looking at Southern California example. So this is from the San Diego County region. Below is the 8-station index, which is from Northern California. On the right side of the screen is looking at Nevada. So on the top is from Clark County, so the Southern Nevada region. And the bottom is from Reno, Carson City, so northeastern Nevada. And what you're looking at is this dark blue is the amount of percent of normal precipitation for 2/3 of all the years. The dashed line is the average, and then all the years are shown in this light blue. So what you can see for both the southern portions of either states, it was incredibly dry, as mentioned before, and then we did have some storms in January. And so for San Diego, we're about 16% of normal. For Clark County and Las Vegas area, we're about 30% of normal. In the northern regions, it was a bit different. The start was not so dry, and that there was towards the end of or early November. In November, there were some rain events, but then it dried out through much of December. And then we had a couple events in January. And that is similar, though the steps, the big events were biggest in Reno, Carson City. There were a couple 1-day or 2-day events. And for the 8-station index, for both the northern 8-station index in the Reno, Carson City area, about 35% of normal. And if you want to dig into this more, there's a lot more information, and here's the website where you can see different regions where this is being calculated for and tracking throughout the water year. So this is just another way to look at it instead of station specific. This is on the left is showing the water year to date departure from normal in millimeters. And so as you can see throughout much of the region, except some here in the middle, that we are drier than normal, ranging between about 1,000 to 250 millimeters, which is about 500 is about a little less, about 20 inches. And then on the right-hand side, it's just a percent of normal because in the northern regions get so much more rain. But you can see in terms of percent, we're about 25 to 50% of normal throughout much of the area. So because we've had such a relatively dry start to this water year, this figure is showing what are the chances of reaching normal precipitation. And so this is using climate division data provided by NOAA as of January 1st, 2018. At the top, obviously, is California. The bottom is Nevada. The first panel is a water year to date percent of normal precipitation. Again, you note that the southern regions are a lot lower than the northern regions. And then if you move over one, these are the odds of reaching 75% of normal precipitation. And so given the precipitation that we've had thus far, and based on historical data, how likely is it that we'll reach 75% of normal? And for the northern part of California and most of Nevada, it's still above 50%. Southern part of California drops down to between 30 and 50%. The odds of reaching a normal water year, so average water precipitation, has dropped down quite a bit to about 20% or less throughout much of the states. And then actually reaching over 100%, it's very unlikely. It's less than 10% throughout most of the states. So this, oops, skipped ahead too far. So this is a similar figure showing a similar information, but it's based on station data. And then because we did get some big rain event, particularly in Southern California in early January, the question was how did this improve the odds of reaching a median water year? And so this is just looking at, on the left side is before the early January storm, what were the odds of reaching the median water year? And then on the right-hand side was after the storm. And as you can see, for a lot of Southern California, the odds increased of reaching the median year. Also along the coast, the odds generally increased. There's a couple places in the inland where the odds decreased just a bit, in the sense that they didn't get much precip from the storm, and it's farther along into the water year where the big events normally occur. But overall, the odds generally increased from that storm of reaching 50%. So, but they're still generally in the between 20 to 30% for most of the region. I'll just briefly touch on temperature. So overall, it's been a relatively warm start to the water year. The figure on the left is the water year temperature anomaly. So this is from October 1st to yesterday. As you can see, much of the region is between 2 and 6 degrees warmer throughout both California and Nevada. And then on the right side is actually looking at the 30-day temperature anomaly, so just over the past month. And note that there is a slight difference in the air bar, or in the color bar, excuse me, and that much of the region is actually between 3 and 9 degrees Fahrenheit warmer. And then there's some parts in particular that are even warmer than that in central Nevada. So this has implications for snowpack, also evapotranspiration in the region as well. So touching on that, with the low precipitation and the warm temperatures, what I'm showing here is snowpack. There's two different ways of looking at it. What you're seeing on the left is that model snowpack, and it's showing percentiles. And so what you see in those red colors, that it ranges between, in some of them, the snowpack is in the 1% lowest that it has been over the period of record, whereas other stations here in the central Sierras is about between 20th and 35th percentile, so meaning it's in the 20th to 35th% lowest years. But generally, the snowpack is low throughout much of the region. The figure on the right is showing first station specific data, and so it's not modeled, so you can actually see the observations, and the observations correspond to what the model data is showing. And this is both a combination of the very low precipitation generally, and also the warm water year we've had thus far. So now I'll touch on where the reservoirs are. This is a figure that we've shown on several of these climate and drought outlooks, and provided by Mike Dettinger. And so if you look at the bottom, you can see this is where the normal reservoir levels are for 28 Western Sierra reservoirs. And so over here, it's showing where the reservoir locations are. And this red line is the current, as of January 15th, reservoir levels in those 28 reservoirs. And one thing to note is, because 2017 was such an extremely wet year, the reservoirs did start above normal. But as we go into thus far a relatively dry water year, they're reaching close to normal. The gray area in this black line is the reservoir plus snowpack. So this is the addition that snowpack adds to the reservoirs. And in much of California and in northern Nevada, the reservoirs are used as a natural reservoir, or the snowpack is used as a natural reservoir in the sense that it holds the water during the winter and then releases it during the spring and summer months as the snow melts. But this year, because snowpack is so low, the amount of water that is stored in the reservoir is very low, which is shown by this orange line. And to combine, they are still well below what the reservoir plus snowpack normal would be for this time of year, which would be up here. So this figure is showing Lake Tahoe, and it started in January 2015. And so during the drought years, you see how Lake Tahoe was much lower. And then during the extremely wet year of 2017, the reservoir, or Lake Tahoe, increased quite substantially. But since then, seen a decrease in the reservoir levels. There was a peak or an increase during some of the November rains, and then has since continued to decrease. But relative to where it was during the 2014, 2015, and 2016 dry years, it is much, much higher, in large part to the really wet 2017 water year. And the last thing I'll show is from the Colorado River Basin, is how we're doing. And I realize this is outside the California, Nevada domain, but because so much of the water, especially in southern Nevada and southern California, rely on Colorado, I thought it was worth showing. And this is from Metropolitan Water District that puts the data together. But as of right now, the upper Colorado River Basin is at 62% of normal. And so you can see the different water basins, what percentage they are overall. And then the figure up here is the Lake Powell storage levels starting in January of 2011 to January of 2018. So it's still above where it was during some of the particularly dry years previously. whereas Lake Mead storage is, again, the 2017 was a bit higher, but it's nowhere near where it was during 2011, which was a much wetter year there. The last thing I'll touch on is soil moisture. Probably not that surprising given the relatively dry water year we've had this far. And in addition to the warm temperatures, most of the soil moisture are in the lower percentiles. So some of areas in the Central Coast and the valley are between 20th percentile and below. So throughout the years, these are the 20% drier years. Part of western Nevada is extreme. The soil moisture is extremely low in these areas. So this is just the combination effect of the low precipitation and also the warm temperatures. So that's a brief summary of where we are currently. So it was a dry start to the water year. Overall, it's still 15 to 35% of normal. The probability of reaching normal this water year is between 20 and 30%. Overall, this water year has been warmer than normal by about 2 to 6%. SWE, or the snow water equivalent, so how much water is stored in the snowpack, is in the 5th to 20th percentile. So again, it's low, a combination of the low precipitation and the high temperatures. The reservoir in California is currently about normal, but the snowpack is low, and so combined, they're much lower than they are during over the historical average. And the Colorado River Basin is at 62% of normal. So that's all I have on the climate and weather update. I can turn it back to Amanda now.
All right, thanks, Julie. I forgot to mention at the beginning that we do plan to hold most questions for the end. I'll try to catch them along the way as we can, but for sake of time, I'm going to move over to our next speaker, who's going to give the Drought and Climate Outlook, who's Shrad Shukla from UC Santa Barbara, and also a member of CNAP.
Thanks everyone for joining in. This is Shrad Shukla. I'm a member of CNAP group, physically based in UC Santa Barbara. Today in this presentation, I'll focus on the drought and climate seasonal outlook. So first thing I wanted to highlight is this product from Climate Prediction Center, CPC. This product is called Seasonal Drought Outlook. So basically what this product does, it tries to answer the question, which is the regions that are already in drought, according to the US Drought Monitor, and Julie showed those maps in her presentation as well. Will those regions experience persistence of drought, or the drought will remain but improve, or drought will be completely removed, or are there chances for new development of drought? So basically, it only focuses on the drought outlook, says nothing about the above normal rainfall or flooding and so on. So for California and Nevada region, as you can see, what's being forecasted is that several of those counties that are currently in drought, such as Santa Barbara, Ventura, parts of Los Angeles, Orange County, parts of San Diego, and Imperial County, they are likely to remain in drought over the next 3 months. And so the outlook is also from January to April 30th. There is also chances of some new development of a drought as well that's being predicted. So that's the kind of seasonal drought outlook over the next 3 months or so.
Hey, Shrad,
so in
your first slide only. We haven't seen your next slides yet.
Oh, really? Let's see. I think this problem happened last time too. Can you see my second slide now?
Yes.
Okay. Yeah, I think this problem happened last time too. Okay, I'll just move the slide. Should I repeat this slide again?
Yes, please. But you can do it quicker, probably. You don't have to do too many details.
So basically, the key message of this slide is that the Santa Barbara, Ventura, part of Los Angeles, all the other counties that are currently in drought, over the next 3 months, which is January to April or so, they will remain in drought, and there are regions where drought development is likely. So in the rest of the presentation, I'll focus on different types of forecasts and also kind of provide a brief descriptions of how they are generated, their source, the skill of those forecasts, and also where to find them. So I'll mainly focus on the large scale climate forecast, ENSO, also focus on precipitation and temperature forecast, and finally hydrologic forecasts. So starting with the ENSO forecast. So before we get into ENSO forecast, just wanted to provide a kind of brief refresher for most of you about what ENSO is. And this material comes from the IRI based in New York. So basically, ENSO describes the natural year-to-year variations in the ocean and atmosphere in the tropical Pacific about this region ENSO. And typically when the temperature in this region of the Pacific Ocean is above normal, this event is called El Nino. And when the temperature is below normal, the event is called La Nina. And these are just two figures from two extreme El Nino and La Nina years, just to give a sense of where the abnormality in temperature occurs and what it typically looks like. So why do we care about El Nino and La Nina or ENSO events? So here is just a map that indicates the typical influence of ENSO on climate. And I must highlight the word typical here because depending on other climate signals or what's happening, say, off the coast of California, the response of these events on rainfall in California could be different as well. So just to highlight that typically during an El Nino years in Southern California and most part of the Southern US, we typically see wetter than normal rainfall season. And similarly for La Nina, typically we see below normal rainfall in California, Southern US, and so on. So now, what is the current forecast for ENSO? And this forecast comes from CPC and IRI. And in this bar map, the blue bars indicate the likelihood of La Nina. The red bars indicate the likelihood of a El Nino event, and the gray bar indicate the probability of a neutral ENSO event. So as you can easily see that over the next 3 months or so, the likelihood of the La Nina events is much higher. And here I actually have listed the numbers here. So for JFM, for example, January to March, the likelihood is about 85%, then it decreases to 3%. So at least I think it's fair to say that through April or so, there will be a La Nina ENSO state. And again, the source of this forecast is from IRI. So another way of looking at it is through dynamical forecast systems. And here I'm using the forecast from North American Multi-Model Ensemble System. So these two maps simply show the, on the left, the likelihood of the SST anomalies in this region being below normal. And on the right, it just shows the kind of a average SST anomaly. So again, you can see that over the equatorial Pacific, there is a higher chances of below normal SST anomaly, which is again forecasted by NAPA. So again, now the question would be how skillful are these forecasts? So this is a result from a study that came out last year. And I know that this is a busy part, but I will try my best to describe it. So basically, what this figure shows is the skill of forecasting. And so blue colors mean high skill, red colors mean low skill. So for any given month of the year, these dots show the level of the skill with which the ENSO state during that month can be forecasted. So for example, if we focus on February, the 0 indicates here that the forecast of February ENSO state was made in early February. And then as we move away from this, the lead time increases. So the next forecast was made in January, December, and so on. So basically, the key message here is that the skill of forecasting and so for late fall months and early winter months is very high, and in some cases, at least up to 6 months or so. And now the second question is, well, how well can we forecast the ENSO state for, say, next water year? The answer would be that we'll have to wait up to at least up to mid to late summer or so to be able to say something skillful about the state of the ENSO in next year. Now, focusing on the precipitation and temperature forecast. So I wanted to start with a short-term precipitation forecast because it looks very active. This map comes from the CW3E group in UCSD, and the forecast was actually generated by NCEP's Weather Prediction Center. According to this figure, over the next 7 days or so, there are several regions in Northern California that are expected to get above 1 inch of rainfall. And there are some places where the rainfall could be 2 to 5 or even higher inches in 7 days or so. So obviously, the next question would be, what is this rainfall going to do with the current deficit of rainfall we have? So also wanted to just show you a map that I think Julie has already shown us. And the map on the right shows the deficit of the precipitation since the beginning of water year. So we can compare this map, which shows the deficit in inches, with this map that shows the rainfall over next 7 days or so. And we can see that, of course, it will be very helpful to get this amount of rainfall, but there will still be places where the deficit will still remain. So for example, in parts of Northern California, deficit is about 9 to 12 inch, and expected rainfall is about 5 to 6 inches and so on. So there will still be some deficit of rainfall remaining after this series of storms. And that's assuming that the rainfall, this forecast map comes true. So next, focusing on the not the short-term forecast, but about a 3 months outlook. So this is a forecast that comes from, again, the Climate Prediction Center. And this map shows the likelihood of the rainfall in being below, above, or normal scenarios. So for Southern California and Nevada, we're seeing that there are parts of the Southern California where the chances of precipitation being below normal is about 40%. And in other parts of Southern California, as well as Nevada, the chances of rainfall being below normal is about 33%. Not much signal for Northern California, so this just indicates that there is really no good signal to indicate if the rainfall will be in any of this tertile categories. So less confident forecast for Northern California. Again, if we look at the same precipitation forecast over the next 3 months or so, but using dynamical forecast models, I'm using, again, NMAB North American Multi-Model Ensemble. So this also indicates that there will be dryness in the seasonal rainfall over the next 3 months over Southern California and Southern Nevada. In terms of probability, the values of likelihood is smaller than what we saw for CPC precipitation forecasts. Now, so one of the reasons why we are only showing kind of a small probability of any signal, say below normal in this case, is because all of these models, in this case about 7 models that go into generating NMME ensemble, they all are predicting different kind of response over California and Nevada. So for example, there are models that are predicting above normal, kind of a strong anomaly, versus there are other models that are predicting a strong anomaly of below normal rainfall. So there is substantial variability in precipitation forecast among individual models. So now again, the next question would be how skillful these models are. And in this map, the kind of green color shows the higher skill, white or yellow color shows the low skill. And as you can see, that typically most of these models are skillful over Southern California and Southern Nevada, but not so skillful over the Northern California region, which is of course the more important part of the region in terms of rainfall. So now moving on to temperature forecast. Again, starting with the CPC's seasonal temperature outlook. And according to this outlook, in parts of Southern California and Southern Nevada, there is more than 40% chances of above normal temperature. In some other parts of Southern California and Nevada, we're seeing about greater than 33% chances of above normal temperature. NMME forecasts also indicate similar above normal tendency of rainfall of temperature over next 3 months or so. But one thing to highlight here would be that the temperature forecast skill at this time of the year is negligible. And this is what is being highlighted in this series of figures, where we're showing the skill of each of the NMME models in forecasting the temperature over next 3 months starting January. And as you can see, in most cases over California and Nevada, the colors are either yellow or white, which indicates that February to April temperature forecasts are not very skillful. So now moving on to the hydrologic forecast. So first I wanted to help answer the question about which is how well can we forecast water supply in summer and so in starting in January. So here's some nice results from Pagano et al. In 2004 that just shows the comparison of the water supply forecasts made in January versus April. So this basically shows the comparison in the skill of the water supply forecast made in January to April. So as you can see that as we move ahead in the season to the spring and late spring months, the level of skill improves. So the first message is that the skill of water supply forecast issued in January is low, but the skill improves in late spring. And again, the next figure here indicates that the difference in the skill of the forecast of water supply made in April versus January has to do a lot with how much fractionally it rains in January to March season. So that's because of the lack of skill of forecasting water supply in summer at this time of the year. I'm only focusing on the forecasts over next 3 months or so. So there is this, these forecasts are made by Environmental Modeling Center, and they just show the forecast of soil moisture percentile for January, February, and March. And these forecasts are made in December, so they don't account for the rainfall that we received in early January in Southern California. So basically the message is that over the next few months, in majority of Central and Southern California, there will be below normal soil moisture. And as we move away from the season, these forecasts diverge to normal. So you will start to see more of white colors in these figures. Finally, another thing that I wanted to highlight here, and these forecasts come from, these soil moisture forecasts come from University of Washington Surface Water Monitor. And they are generated by using 2 different methods. In the first method, basically all years from the history are used to generate scenarios of soil moisture, which is on the left. In the right, only those years that have similar ENSO state as the current year are used. So only the years that indicate La Nina. So now as you can easily see the difference between the forecast on left versus right. And the difference is that the forecast on the right indicates drier soil moisture. So basically the message is that if we only use La Nina years from the past, the soil moisture is likely to be even drier over the next 3 months or so. So now, in summary, CPC's seasonal drought outlook indicates persistence in drought in parts of Southern California, with some new drought development likely in parts of Central and Southern California. Official ENSO forecast is for La Nina. These ENSO forecasts are most skillful for fall and winter months and up to about 6 months in advance. Below normal precipitation is likely over the next 3 months for parts of Southern California and Nevada, and no clear signal for Northern California. Temperature forecast skill for the upcoming season of February to April is negligible. Also, skill of water supply outlook in the forecast generated in January is low. And finally, the soil moisture is likely to be below normal during the next 2 months or so. So here is just a list of the sources through which I collected those forecasts, if you wanted to dig deeper into details. I think that's the end of the presentation. Thank you very much.
Great, thanks, Shrad. As I mentioned before, people can put their questions in the questions box. We don't have any right now for you, Shrad, but we'll see if we have any towards the end.
Okay, thank you.
Yeah. And our next speaker is going to be Tim Brown from the Western Regional Climate Center. Tim, I can see you're there. Were we planning to have me give you the screen control?
However, go-to works.
Yeah. Okay, I'm going to pass it over to you right now, and then you'll see a little accept box.
All right, good. So good morning, everyone. And I'm Tim Brown, Director of the Western Regional Climate Center. And I'm going to give you a very brief overview of the Northern and Southern California 2017 wildfires. It was actually quite a year across the country, particularly in Northern California, Pacific Northwest, and Northern Rockies area, even before October and December, which will be the focus of what I show you here. And already at that point, there'd been large amounts of area burned and maximum resources used across the West. And then came October in Northern California. No doubt you all know about this, seen photos and video footage. The NAPA Fire, so just in summary, again, 44 fatalities, at least 8,900 structures destroyed, 90,000 evacuations. At peak deployment, there was 10,000 firefighting personnel on scene, including folks from Canada and Australia. At least $9 billion in insured losses, and the cause still under official investigation. We know it's not lightning. We know it'll be a human factor of some type, and we'll wait and see what those results show. This map over here highlights really the four largest fires, and the one that's made the most news probably is the Tubbs fire here. So the climate and weather background behind this, I think we can show that there's probably really a flash heat and flash dry in late September and early October. That was a major contributor. It did follow a wet winter and spring, a very hot summer, and Diablo Wind was a major driver of these fires. Looking here at the Drought Monitor map for around the time of the fire, from the drought perspective, this area is not depicted as under any particularly unusual drought conditions. So something else going on there. This plot shows NDVI, Normalized Difference Vegetation Index from MODIS satellite. From January 1 through the end of the year, and the black line being the climatology. The blue line a point basically representing the Santa Rosa area. And you can see back in the spring, here's beginning of April, greenness was getting up there. And so the fine fuels and the brush were responding quite well to that wet winter and spring precipitation. Then it gets down to normal, and then actually from a greenness perspective, it kind of came back up here beginning of October. So again, the question of, say long-term drought, probably need more investigation here, but long-term drought itself may not be a factor going into the Northern California fires, and it had a lot to do with the wet winter and spring. You can also look at this through evaporative demand, and this will basically say something about, or could be related to vegetation stress. This black line represents an index of evaporative demand from early in August through the end of November. So the red line here represents the start of the Tubbs fire on October 8th. And one thing that you can see here is that there was very high demand in the months leading up to the Tubbs fire. But some work by Mike Hobbs at NOAA and Boulder and Dan McAvoy and WRCC has looked at decomposing because this evaporative demand is made up of temperature and humidity and solar radiation and wind speed. So it's of interest to see which one of these was the primary contributor. So here's the same black line, but the red line here now shows the contribution of temperature going into the black line. And we can see that back in August and early September, temperature was an important contributor to the evaporative demand. But actually leading up to the October 8th fires, not so much. Now, if you look at humidity as a contribution back in the early months, that was not a significant contributor. But for a few weeks leading right up to the Tubbs fire, it looks like that low humidity, this value looks positive because it's a contribution to the evaporative demand, but this actually represents lower humidity values. So there's a real drying of the air a few weeks up to the fires, and of course that's going to help dry the vegetation, which was already somewhat dry and curing just through the normal seasonal cycle. So the next thing are the Diablo Wind, and in this animation, if we just focus up here on the Sacramento area, these are Diablo winds, not wholly unlike the Santa Anas. They're easterly and then northerly winds. They get funneled down. They're very terrain-driven, driven by large-scale synoptic patterns. And during the day, the evening of the fires, it was very strong winds. That was an important contributor, probably in part to the ignitions, but certainly to the spread of the fires. This is a model run showing the upper surface and upper atmosphere. The terrain here, of course, terrain is depicted by this gray area. So here's the coast over here. Right here would be the Tubbs fire, and these are wind speeds showing in miles per hour, showing very strong winds at the surface and up through the atmosphere. And basically what these winds are doing are funneling down from the northeast into the Santa Rosa area. And when the fire began, it was pushing the fire front, but also creating a lot of ember storm. And this eventually got into the very urbanized area here of Coffey Park and did substantial damage. Wind gusts 68 miles per hour at the Santa Rosa station. So very strong winds throughout this event. And it was actually more than just in this area for the Tubbs fire. There were actually several others that happened concurrently. A lot of smoke was produced from these fires, and that led to a lot of smoke impacts, health and air quality impacts. There was numerous times of which the air quality was unhealthy to very unhealthy in very urbanized areas, such as the Napa region and San Rafael, Vallejo, and so forth. So it was quite an impactful fire from all perspectives. Well, then you think the season might be finally over, and then December comes along in Southern California, and we have some major fires that break out, the Thomas Fire being the largest of these. There were 2 fatalities in this event, but there were 230,000 evacuations, major traffic disruptions, power outages, school closures, and again, hazardous air quality issues. Now, what about the climate and weather leading up to this event? Notice down here that this is a beginning of December, first week in December, shortly before the fires. And again, there are dry conditions depicted here. And the thing is, this area has had color on the Drought Monitor pretty much since February of 2012. And then they also had a dry autumn, so some autumn rains that might normally come did not. And so your fuels were very much cured and available. And the Santa Ana wind then comes along, and again, you have a similar situation in which if you have an ignition, then you're going to have very rapid fire growth and spread. But the long-term drought is probably, folks are still thinking about this, but there's probably what's happened is that long-term drought may have increased the amount of dead chaparral in the area, because the grass and chaparral dry out every year here, but given so many years of drought, there may have been an anomalous amount of dead material. And then with the ember storm getting into that, that would have also rapidly advanced the size of the fire. One way to look at the fuels is it's called the 1,000-hour dead fuel moisture. It's basically a depiction of fuel dryness for dead fuels, not live fuels, but for dead fuels. The gray line here represents the average throughout the year. The red line, all-time minimum, and the blue line is what was going on in 2017. And leading up to these fires, you can see that the fuel moisture values were running low and actually getting into the record low territory. Just to bring this map back again for the Santa Ana winds, just as a reminder, very strong winds, again set up by synoptic, larger scale synoptic patterns, but strong winds induced by terrain blowing basically from the northeast, and once they get down in this area and there is a fire, it makes it very difficult to control. Here's the timeline of the Southern California fires. And I will say that actually for both events, the meteorology part was very well forecasted. And that was true for the Southern California fires as well. The fire agencies were preparing for the upcoming wind event really starting on Friday, the December 1st. These maps down here show Santa Ana Wildfire Threat Index. This is an index based on meteorology factors, weather factors, but also fuel factors. And the reds are the highest risk areas, orange are moderate. And so the first fire This index threat came out here around this time on Monday. The Thomas Fire began later that day, eventually reaching over 280,000 acres. Then you had the Creek Fire, the Rye Fire, the Skirball Fire, and on Thursday the 7th, it was the second Santa Ana wind event, which was also forecasted well. In fact, they had to add a color. The index was so high to their scale. Then the Lilac Fire occurred. This is a burned area taken from Landsat data draped over a digital elevation model. It's not the full fire, but one reason to show this here is to give you a sense of fire burning in the complex terrain of the region, where the housing developments are, but also that this is a burn scar area, and some of it in here more severe burn than other areas. But now one can imagine if a rain event were to come across these burn areas, that you could have a new problem that's fire related. And indeed that happened on January 9th. This is a picture of the Montecito post-fire debris flow. Basically what you had was a narrow cold frontal rain band, which can occur a couple times a year in Southern California, came through. These things are typically not that large. They can occur and not even impact a burn area, but in this case, it was a direct hit. And that led to extreme devastation in the area, 20 deaths, more than 100 homes and infrastructure destroyed, a 2-week closure of Highway 101, which of course is a major transportation route. So anytime you get these high intensity rainfall events over these burn areas, they are important ingredients for this post-fire debris flow initiation. And lastly, to put it in perspective, this graphic shows you the most destructive fires in California in terms of structures destroyed. And 5, these are the top 20, and 5 of those top 20 occurred this year, with the Tubbs Fire now leading the list. So with that, that's my summary, and I'll turn it back over to you, Amanda.
Hi, Dan, thanks. While I'm changing over to the next presenter, someone did ask us if you could repeat real quickly your explanation why the 2012 to 16 drought likely wasn't very contributory to the October wildfire.
Well, I think that's because given the fuel type in the region, and this is worthy of some further investigation, but that area also has a lot of grassland and shrubs, so there is natural drying and vegetation available frequently. So, and it dries out in the autumn naturally. I think the question is, what did the longer-term drought, what impact, if any, might that have had on the heavier fuel types, such as tree vegetation, even though it was a wet winter and spring?
All right, thanks, Tim. And I encourage anyone to get in contact with Tim if they have more questions. That came from someone at the state of California, so they might have some questions following up for you. With that, I'll go to our last speaker, who's going to be Dennis Lettenmeyer from UCLA. He's going to talk about his tool.
Okay, great. So yeah, we're really tight on time here. So let me run through this. I only need 5 or 10 minutes. Just wanted to talk a little bit, and this overlaps with some of what Shrad talked about. In fact, a good bit of what I'm going to show is based on tools and so on that Shrad put together when he was at University of Washington. I'll just mention this California-Nevada Drought Monitor, which Julie also mentioned. You can go to hydro.ucla.edu and click on Drought Monitors. Real quickly, where does the stuff come from? Julie mentioned it's model-based. The stuff that was shown earlier, I think, was all from the VIC variable infiltration capacity model. I'm not going to go through the schematic there, except to point out I'm going to show soil moisture, what we call total column soil moisture, which is actually 3 layers. Think of it as being the soil moisture in roughly the upper meter or so of the soil column. The model also does snow, and in fact, I think Julie showed a visual from the snow part of the model. I'm not going to talk about that here. This actually relates to something what Shrad talked about. He was actually talking about some of the forecasts and ensembles, which can come from different places. He talked about NMME, also something called ensemble stream flow prediction, which is where you just resample all the historic years and say, you know, we really don't have any particular skill. What happens if you take all the historic years, starting with a so-called nowcast of what we think the current conditions are, at least what the model thinks the current conditions are. Back over to the left of that bar is gridded observations, basically go into the model, run from back to, you know, a couple of years or so. So what I wanted to show here, let me go flip forward to this visual here, because this little band, this came about during the Southern California fires when we were interested in what was going on with soil moisture. And we just took this band, which goes about 50 kilometers or so in from the coast, and that is some number of kilometers north of Santa Barbara down to the Mexican border. And what's kind of interesting about this is you see in October, the white is kind of soil moisture percentile relative to like a 100-year history or so is in the vicinity of the median, and then progressively it gets more and more reddish brown, and those colors are roughly on the red side are roughly the Drought Monitor colors. So when you look at this, when we average soil moisture over that whole area, and you look at it as a probability distribution of where this was starting in October, you can see the red is more or less the middle of the distribution, which is what the spatial plot showed. As you go the 1st of November, 1st of December, on up to December 15th, and actually, my screen is covered over by some control stuff here, but the red has crept down to, by the 1st of the year, the lowest soil moisture of record. Okay, so, you know, the Drought Monitor is showing that as kind of light yellow, and as Tim mentioned, has been for some time, but the Drought Monitor tends to lag a little bit what we see in the model world on both ends, both in terms of how from soil moisture standpoint these droughts evolve. And then last year, with all the rain, we were showing the drought basically gone in that domain much earlier than they had. And there's some rationale for that having to do with groundwater and so on, which is not represented in the model. So the question has sort of come up, and this is really irritating. It would be nice if I knew how to get rid of the.
There's a little orange arrow at the top of that box. If you click that, it'll shrink.
Oh, does that make it go away?
It shrinks.
Wonderful. Perfect. Okay, thank you. So we're sort of wondering, okay, so what effect, and unfortunately this just shows California, but was the January 8th and 9th storm on the soil moisture. And what you see there is up in the upper left is the 1st of January conditions. The 8th conditions, which looks very similar to the 1st. I think what's happened is there may have been a little precipitation. There's an issue with the precipitation of the time of observation on these gauges that are gridded, and there may be a plus minus a day thing in there. But you can see just that one storm has taken a lot of that out of there. You got a lot of whites in there. The whites have expanded and so on. So the thing, it hasn't made it completely go away, but you know, a couple of inches of rain makes a big difference to the soil column, particularly because part of the reason for this is, you know, in late fall, it's normally always dry. Most years are always dry. So the climatology is dry, and exceptionally dry and just dry aren't that a huge difference in terms of millimeter of moisture content. So the other thing we've been looking at recently here is this question of, okay, when you got an anomalously low soil moisture in January, how much effect does that have on the conditions for the winter season? So the correct way to do that, if you go back to the earlier visual showing the nowcasts and the forecasts and how ensembles go into that and so on, would be to just run all the ensembles through it. We were a little bit lazy and said, how can we go shortcut this? And what we did is we took a scenario where we started with the January now 15th condition. So this is post the storm. And we took median winter precipitation and we allocated it in every model grid cell according to the climatological fraction of winter precipitation that occurred in that particular month. Then you have to also do something about the daily sequencing of precipitation. I think we said on average it happened every 3 days. Okay, so when you put the median winter precipitation in, you see progressively what happens. January 15th, that's what the model thinks more or less is now. February 15th, a little bit less. March 15th, there's still a little bit of brown in there, and by April 15th, it's pretty much wiped out. What that has to do with is just there's only so much moisture capacity in the soil column, and if you put median precipitation in, it pretty much makes things go away. We also ran a scenario where we said, okay, what happens if you get the lower 25th percentile through the whole winter season? And in that scenario, you do get persistence clear on through to the end of the winter. And of course, end of the winter, you know, ends up looking a lot like the next fall, modulated by whatever happens with the evaporative demand through the summer. So exceptionally hot summer, you'd expect to have more of that. So I guess the message is in the model world, and I don't think this is too much different than what Shrad showed from the UW surface water monitor, which has some specific differences in terms of the courses of the spatial resolution and so on. But that most of it sort of goes away with median precipitation. If it's below normal, it persists on. Now, there's a bunch of other factors in here. The big one is not showing snow at all, which in the snow dominant part of the domain, you do have this accumulation pattern and sort of the likelihood of getting up to a median condition for the snowpack, and I can't remember if that was Shrad or Julie showed that, ends up by the time you get to the end of January and you're behind, it's pretty hard to catch up. So that's not in here. This is the soil column only. So I'll stop there.
All right, thanks, Dennis. At this time, I'm going to remind people there is a questions box. I know we're a little over time, but we can take a few questions. Always you type those in. While we're doing that, I'll just take a chance to say thank you to all of our speakers for presenting today. Our next webinar for this is scheduled for Monday, March 26th. So as we get closer to almost finishing through the water year, I want to say that we do plan to post the recording, the slides, and a 2-page summary up on drought.gov when possible. In the meantime, if you have questions or need to get materials quicker, you can reach me probably at my UCSD email that's there. It's better than the NOAA one right now. But that's about it, I think, for that. And I don't see any questions yet, besides what we answered earlier. So with that, I'll close the webinar, and I encourage you all to contact the speakers if you have questions or contact me. So thank you, everyone, and thank you to the speakers.